My name is Mint, and I'm here to present the neural network hand crank, a Raspberry Pi-based device that can be used to manually train a network. When I want to say I want to train a network using hardware, I do not mean I'm using any sort of clever tricks like utilizing the GPU to speed up training. What I mean is I'm literally going to tune each weight and bias of the network by hand. So neural networks are the basis of the current machine learning / deep learning revolution. And perhaps the most popular usage is for prediction. You put in some data, such as an image, and they will perhaps predict for you what the image is of. In order to achieve this behavior, neural networks are trained on massive amounts of training data, pairs of input and output data that teaches the network how to predict. This training process is done automatically using sophisticated computer algorithms, without which none of the amazing deep learning algorithms today would even exist. However, in this project, I say screw all that and push deep learning research back 40 years. I coded my own neural networks, loaded them onto my Pi, and then connected several hardware devices that can be used to tune the network. In order to justify the time I spent on this project, I came up with several motivations and potential applications for this inane endeavor. First, I think that the tool can be used to teach undergraduates studying neural networks. As you will see later, the process of manually tuning a network is actually really informative, even if it is super slow. The tactile feedback that one gets from manually tuning a network and retuning it as needed until a satisfactory result is returned can greatly contribute to the learning process. In addition, I think that it would be really satisfying or fascinating to see deep learning competitions of teams trying to manually tune a network that, say, was that had like 1 trillion parameters or something like that. So I'm not going to go into too much background, but the important facts are these. Neural networks pass input data over here through a collection of hidden layers and through a bunch of multiply and accumulate operations before the data gets transformed into the output. The lines connecting each layer is called the weights, and these gets multiplied to the previous layer before they go into the next layer. And then these lines right here are the biases that gets added to each neuron after the multiplication with the weights. When we say we want to train a network, what happens is that the network will be initialized with random weights and biases, and through a process of prediction and then checking to see if the prediction match what the output was supposed to be, the network will update these weights and these biases until the prediction matches. Instead of doing that automatically using an algorithm, we'll just do that by hand, which is possible. For the hardware, I had a Pi 0W. It's somewhere up here. I had from my previous class. I had to solder the GPIO headers to the board, and I attached an extension board for easier breadboarding. I had a few potentiometers, and I really liked handling them. So that's what I use to tune the networks. The output of the potentiometers is analog, which the Pi cannot process. So the potentiometers are hooked up to an ADC module right here, and that converts the analog signals to digital. Here's sort of like a quick rundown of how that works. So what you get from the potentiometers is like 0 to 5 volts, and it basically gets mapped to a range of numbers between 0 and 1023 if you had 10 bits. But my ADC module only maps 0 to 255. So the first potentiometers is going to be used to tune the weights. The second is going to be used to tune the biases. And the third is going to be used to switch between tuning weights and tuning biases. You can specify which you want to tune. The red and yellow buttons are used to flip between the different layers of the neural network. As you can see, there was like an input layer, an output layer, and like a bunch of hidden layers in between. So you can use those buttons to flip through. And the blue and the green buttons can be used to flip through each individual weight and biases, because you have to select the weight and the bias that you want to tune. And then you can tune them using the potentiometers. And there's also an LCD screen that displays what weight you're currently considering. So you can kind of see that going on. So the software, I follow the guide online on how to code your own neural network. I did it this way rather than using a library like Keras or TensorFlow, because there were functions like training and backpropagation that I really didn't need. Coding the network manually just gave me more control. It also allowed me to implement my own functions, such as the get and set weight biases functions. I mean, this is the main sort of mechanism that is going to be used to edit and change and view the weights of the network. The weights and the biases of the network is just an array of numbers. So accessing them and changing them is as easy as just indexing into an array. In order to map a potentiometer value to a specific weight, I divided a range of values from -2 to 2 evenly by 255 values. As you remember, when you tune these things, you either get 0 or all the way up to 255, and you can sort of map them into this range of values. I picked -2 and 2 because just from experience, weights for neural networks are usually pretty small. So you'll probably be good with -2 to 2. You can always change this later. And then finally, I coded a simple while loop that would continuously monitor my hardware for inputs. So if a button is pressed, then we either loop through a layer of the network or loop through a weight. And if a potentiometer is turned, then we tune the weights and the biases. You can see the process in more detail here. So if button two is, I believe it was the yellow button. So if it's pressed, then you loop through the layer. If a potentiometer is turned, then you just call neural network.set weight into that new weight value and then you output what the new weight value is. Okay, now to the fun part. The first task that I used as a proof of concept is the XOR function, and it's shown by this table here. I'm pretty sure we're all familiar with it. This is the network that can be used to solve this task, and this has an input layer, one hidden layer, and an output layer. So you put the first input here, the second input here, and that should come out output the XOR of those two inputs. The arrows represent the weights, and there's a bias that gets added at the hidden layer, but it's not shown here. And the weights and the biases are what we're tuning with my tool. This is the solution set of weights and biases that can be used. This came from the deep learning book. I know showing them is kind of counterintuitive, but I needed a way to verify that my tool was indeed working. So I can show you sort of like a before and after process. So this is before tuning the network. As you can see, x00 is supposed to return 0 for XOR, but it's 1. So that's not right. 0, 1 is 2 instead of 1. That's not right either. 1, 0 is, well, you get the point. So, so now we can call a tune function to start tuning the weight and biases. So what you're seeing right now is that we're looking at layer 0, which is the input layer, and we're looking at this particular weight at that index, which should correspond to this guy right here, and which should correspond to this arrow right here. So now that we've selected it, we can use the potentiometers to sort of tune. And I think this is my favorite part of the project because it's just really fun to sort of tune this thing around. And so you see me tune it to 1. So I'm basically going to tune everything to the correct configuration. See here, I erroneously moved to layer 1. So I flip back to layer 0. I move on to the next weight, which is this guy right here. And it should be this arrow right here. And I tune it, and I tune the subsequent weights. And so after, that whole process of tuning took about 2 minutes. This is tuning the bias. Let's test the network. And so now 0, 0 comes out with 0. 0, 1 comes out with 1. 1.2, it's not perfect. I mean, neural networks are not perfect, but they are great approximators. So you can keep tuning this until you get it perfect. You see it's like -0.03, which is close enough to 0. But obviously, you can just keep tuning it until you get it working. The last demo is a NAND gate because NAND gates are interesting because they're universal gates.
Nor was 2.
What?
Nor was 2.
Oh, that was XOR. The previous one was
XOR.
XOR.
I thought it was NOR. Thank you.
Yeah, it was XOR. So I went in this one blind. Like I tuned this thing from scratch. So it took me about 15 minutes, and I can't believe that I actually was able to do it. But this was really the learning process for me. So first, I decided that the network should be similar to the one I used for my XOR example because of how close the two functions are. They only differ in the output for 0, 0. For XOR, the 0, 0 output should be 0, and for NAND, it should be 1. The rest is the same. So I started with the same network. And then I initialized the network with the same set of weights that I used previously. And then I just sort of went out from there and started tuning it. For the next 14 minutes, I manually tweaked each weight and bias of the layers to figure out the effect that each one was having on the output. I cannot really say I remember which weights are responsible for what, but there was a point when the whole process kind of clicked when I found the one weight that, when held constant, gave me the output that I needed. It was kind of like solving a Sudoku puzzle through an iterative process of trial and error. I was really happy when I finally found the one weight that made everything work. Um, so this is just the early stages. And so if we look over here, x00 is equal to 0. That's not right. So if you watch the whole video, you'll see me go through this process of like manually tuning each weight and then checking the output over and over and over again until finally, this is still tuning it, I think. Okay, so finally, 0 NAND 0 is 1.03, 10 NAND 0 is 1.08, close enough, 0.01, and then 1 NAND 1 is negative 0.12. You could keep tuning it until this is perfect, but I had already sunk 15 minutes onto this, so I had better things to do, so I just kind of stopped. But it's just a good proof of concept, I think. So and yeah, that's it. So this is the conclusions. I had a blast doing this project. From learning how to solder to making something so stupid it's brilliant. This was an incredibly rewarding experience for me. I think the biggest takeaway is the experience of emulating how neural networks are trained. I was able to experience firsthand the iterative cycle of feed forward and then back propagating, with air quotes, the errors to fix the weights until something worked. That aha moments when you get that one weight that makes the whole network work is really satisfying and illuminating. Here are some potential thoughts for improvements. The first obvious improvement is to try out more hardware pieces. Maybe there's an input device out there that is more intuitive than a potentiometer or a button. In addition, I think I would definitely revise the visualization aspect of the project. Displaying the weights one by one on a 16 by 2 LCD screen seemed fun at first, but it quickly became super intuitive and super just so slow. So if we had a GUI that could print out the whole network as you're tuning it, that would probably be a lot more engaging and more fun experience. I also want to make the tool a bit more flexible and scalable. Maybe turning it into a library that serves as an interface between neural networks and hardware input devices. You should be able to specify the architecture of your network and the type of hardware inputs you're hooking it up to. And then the library should just automatically link those two together. In this project, I had to write all the code myself. Next, I want to try my tool on larger and more complex networks. The tool works with networks of any size, so long as the hidden layers are of the same dimensions. But really, it would be interesting to try it on other architectures. Like this chart here, this neural network zoo. There's so many network architectures out there. Try it on a convolution neural network, usually used for images, or a recurrent neural network used for sequence data like text. And try it out on more complicated tasks than just NAND or XOR, like the image recognition task in this. But yeah, that concludes my presentation in 15 minutes. And thanks for listening. I wrote this whole presentation on my blog, so you can read about it here. But yeah, that's it.